All right, today we're going to be looking at writing and solving equations from real-world scenarios with an introduction and some examples. This deals with the dreaded word problem that students often have a hard time with in mathematics. And hopefully some of these tips and strategies I'll give you will make these word problems a little bit more accessible, a little bit more straightforward, and not quite so painful for you. And the first tip I have for you is my favorite, what I think is the most important. In any word problem you're dealing with, look for the question mark. What is it specifically that you're trying to answer? Often there's a lot of information given, and then there's a question that's being asked. So what is it that you want to know? What specifically are you trying to answer? And then that is going to be used to define your variables. Okay, and I'll model that for all the problems we're doing today. The other strategy is to carefully translate English to mathematics, and I will, you can see the chart on the screen right here. I'll help you fill that in and look at some words that translate into addition, subtraction, etc. Definitely solve and check it. That's often the easiest part of it, is actually solving and checking. But then take a moment and just pause and think at the end. Does your answer make sense? Does this number make sense in the context of the problem? All right, so let's get started. We're going to first just brainstorm some words that we can use to translate between English and mathematics. So you can see my 5 columns here representing the 5 common mathematical symbols or operations that we deal with in Algebra 1. And let's just start brainstorming. So obviously this is a plus, but we might use the word and or sum or total. Sometimes also represents an addition. Obviously add or addition. So those are a few that represent addition. For subtraction, you might see some words like less than, obviously minus or subtract. You might see the word difference. That's all I can think of right now. During the course of this video, we might brainstorm some more and come back. For multiplication, in algebra, we often represent multiplication as a dot, so it doesn't get confused with the x we often use as a variable. Obviously times, multiply. I think if you see this phrase for each or per person, something like that. But my favorite multiplication one is the word of, and that often comes into play with percentages. If you're talking about 25% of something, it means 0.25 times that something. For division, slash or the typical division sign, obviously divide, quotient. Let's go back to multiplication. You'll see the word product for multiplication. Sometimes the word into or equal parts or split. Those all represent division. Okay. Probably the most classic one for these brackets, for the parentheses or the square brackets, which really mean the same thing in mathematics. The most classic one is quantity, or maybe quantity of something, okay? So if you see something that's like 5 times the quantity x plus 2, that implies that we're dealing with 5 times the quantity x plus 2, where the x plus 2 are in the parentheses. So that's the biggest one to look out for there, is the quantity word. Let's go ahead and solve some problems. So our first example is a local gym charges a monthly membership of $45 plus a one-time application cost of $10. And there's a competitor gym that charges a monthly membership fee of only $35, so it's cheaper per month, it looks like, though their application is $65, so it's more expensive initially. How many months should I attend the second gym to make it a better deal? Okay, so let's look at some of these words. We have a plus in here. Monthly implies a multiplication because it's sort of a per time. It's a $45 per month, and that's going to apply to both gyms, it looks like. So it looks like we have some multiplication and addition as well. And of course the of implies that multiplication also. So let's define variables here, and let's call it t here equal time in months, and I'm actually going to have this be where the costs are equal. Okay, so if we go to the gym this many months, we'll be paying the same amount to either gym. But if we go for more months than that, then the second gym should be a lesser cost. So we can write out $45 for every month plus an application fee of 10, and let's have that be equal to 35 for every month plus an application fee of $65. Okay, let's subtract 35t from both sides, and I'm going to model here doing some simultaneous subtraction. So we can do 35t from both sides, and we can also subtract 10 from both sides. Let's try to do that in one step. If that's too much for you on your own, feel free to split that up into different steps for sure. So we have a 10t, those cancel, equal 55, whoops. And we're going to divide both sides by 10, and we have t equals 5.5. So it looks like if I went to the gym 5.5 months, I would pay the same amount to either gym. So I would say my answer would be 6 months or more. And let's assume that we need to pay for a whole month at a time. Okay, next one, sum of 3 consecutive numbers is 369. What's the smallest of these numbers? So let's define our variables. Let x equal smallest number. This is a classic problem where you're tempted to just guess and check, okay? And you plug some numbers in your calculator, see if it works, and then you adjust from there. But let's do a little bit of algebra. So whenever numbers are consecutive, it means they differ by 1. So we have x and x plus 1 and x plus 2 equals 369. Okay, so we have 3 x's on the left plus a 3 is 369. And we can subtract 3 from both sides. 3x equals 366. And let's divide by 3 here. So x equals 366 divided by 3, 122. So we could check that is 122 plus 123 plus 124 equal to 369. And I'll check that on my calculator. Yep, and it checks out. So it looks like we're good. So x is 122. So just to connect to what we did earlier, we are dealing with a sum, and we defined our variables to answer the actual question being involved. Okay, last problem for today is this one. A retail clerk determined that they collected $870 in closed sales during one day. They knew that closed sales made up 2/3 of the total sales that day. What were the total sales? Okay, so I've been 870 in clothes. I have this statement here, which is going to be useful, 2/3 of the total. And once again, that word of shows up to mean multiplication. And then the specific question we're being asked is what's the total? Okay, so we can use, I'm tempted to use S for total sales, but S often looks like a 5. So let's use T for total sales. So let's let T equal total sales. Okay, and let's write out a mathematical statement. Closed sales, which are 870. So let's see here. So this 870 I can really just plug in for closed sales. So 870 made up, which means equals, 2/3 of, which means multiplication, the total sales. Okay, we can do the reciprocal process here. Let's multiply both sides by 3/2. And let's see what we end up getting. On the right side, this 2 cancels with that 2. These 3's cancel, so we're left with just a t on the right. 870 times 3/2, that's 870 times 1.5. And we have $13.05 for total sales. And the thing I want to model quickly for this one is to just think, does that answer make sense? I didn't do that real thinking process for the prior two. Let's see, does $1,300 make sense for total sales if about $900 of those were closed sales? Yep, it seems like it makes sense. It's a reasonable answer. And that's a good place to stop right there.